So here let us say one thing. Actually, there are so many aspects for learning. All right, but the way I am viewing it, I am viewing that the supervised learning is the same as classification. All right, so that is going to be my viewpoint. That I'm saying that the purpose of the supervised learning is to be able to do classification. Okay, so that is the way I'm viewing it. All right, so this is the theme which will be throughout this kind of presentation. Towards the later end of the talk and discussion, I would like to show you some other research articles and some textbooks which are in this domain. There are some advanced textbooks which are in this domain, which would be very helpful for people who wish to get into the research domain and things like that. Okay, so with that, let us just see like whatever we are going to be taking up today, more or less. Actually, this is a very vast topic and subject. Okay, I don't know really how I can do justice to it in this kind of limited time, and that too in this manner. So okay, so let's see what we can do. Um, Somehow, okay, see that I have seen the brochure and I'm seeing that lots of very good, excellent speakers have come and spoken so far, and then some subsequent very good speakers also would be there. All right, so I'll just be looking at one small aspect, that is the this classification approaches. All right, so here you can see that there are some um, approaches which are being mentioned. That is, what are the basic concepts which are there related to the classification, and one of the in machine learning, one of the very important methods is a decision tree approach. Okay, so given certain data, how do we induce the decision tree? Okay, so decision tree meaning that we take a sequential classification and we try to divide the data set which is available to us into smaller and smaller groups such that every group is very homogeneous. Okay, then one of the well-known statistical methods is the Bayesian classification method. And here again, Bayesian classification by itself, maybe I can talk for half of the day. Okay, so like this, these are all very big topics, and it takes quite some time to go into details of each and every one of them. However, today we'll just try to see some kind of an overview so that people can get some idea, and then later on, based upon their interest and such things, they can take up some further studies and all. Okay, so with that, I will go forward. So before we come to the classification and all that, we should know that there are different types of data, and I will just be going a bit fast over this aspect. No, because the data introduction is necessary because we are dealing with multi-attribute data, or we are dealing with the multivariate data. Okay, if you are talking statistical terms, we are dealing with multivariate data. If we are talking in the database kind of terminology, we are dealing with multi-attribute data. Okay, so that is the type of thing which is there. And the data and the variables also have their characteristics. Okay, I think these kind of things are very elementary, that the variable means it is varying from one member of population to another. So I will not pay much distance for that. So that, okay. Then when we come to the types of the variables, then you can have that, numerical variables or categorical variables. And categorical variables means that, say like Sunday, Monday, Tuesday, the days of the week, these are categorical. All right. Numerical variables means like what is the temperature today? So 25 degrees centigrade, something like that. So that is a numerical variable. Okay. So that is to give you some idea. And then even the numerical variables, discrete, continuous, and then you have scales, and all these kind of things which are there. And these are actually some kind of a background which we consider when we are looking at the data which we have got. Okay, I will skip these kind of things. They are nominal scales and ordinal and things like that. Okay, so I'll skip that. Then when we take up the social sciences data, or we're talking about social media and whether somebody is liking something or not, so then we want to do a survey, and then we have a question, and for the question we record some answers which will be on a 5-point scale. Okay, so like this, it just depends on the survey. Some surveys have a 10-point scale, but the way it will be that it is, say from a, middle standpoint. On one side, it is leaning towards a positive approach, and the another side will be leading to something like a negative approach. These are the kind of things which are helpful. Say like if you want to collect all the tweets, and we want to collect all the tweets, and we want to do a classification that the sentiment analysis, whether the tweets are showing us that some topic is good or bad, and so like that it is possible to collect all the tweets and do some analysis on them and gauge a sentiment from the tweets. Data sets are there and data tables are there, just like this kind of data table which we have. So this is a typical data matrix arrangement which we have, and in the pattern recognition and other kind of thing, we call that the columns are arranged as the features, and the objects, various objects, are called as the rows. And this is again a typical data table which is, say, for some medical data. So these are okay. Once we are having the data, then how do we do classification? Okay, so or how do we do how do you find that some objects are similar and some objects are not similar? So we have to be able to define the similarity and dissimilarity methods. Okay, so numerically, we need to be able to say that some two objects are similar, and then we have also another the same way. We should be able to say that something is dissimilar. Okay, so this, and then we have the notion of proximity. So if two objects are very similar and they are belonging to the same class, they should be put with the same class level, then they should be having high similarity or low dissimilarity. Okay, so that is the idea. This is the very well known formula which you all have seen since when you started reading the coordinate geometry. Okay, so now only thing is that here I am extending it to uh, that, say, some k objects, I mean, say k attributes are there, okay, and then we can find out this. All right, so basically your Euclidean distance is when it is, that is just is equal to, for a plane, it is, say, like just 2. Okay, so rather, okay, I mean, there is another one which is a generalized distances. So this is say for the k dimensions, sorry, and for k dimensions this is the Euclidean distance. Okay, like this. So we can this is some kind of example. One can compute the distances and you can come up with a distance matrix. These distance matrices are very useful when we want to do nearest neighbor classification. Okay, nearest neighbor classification is a very intuitive approach, and almost everyone can easily understand that. Okay, just what we do is that for doing the classification, we will find this table, and then we look at what is the smallest entry in this table. If you see the smallest entry in this table, this is between P3 and P2, which is a distance of 1.414. Okay, so P3 and P2, as you can see in this figure, they are very close by. All right, they're compared to P4, which is a bit distant, and P1, which is still more distant. Okay, so visually you can see that the distance or the similarity which is computed is allowing us to say that these two should be forming some kind of a set. Okay, and they are a bit more cohesive as compared to this P4 and P1. So therefore P2 and P3 should form one set. Okay, so like this, the notion of distances is allowing us to do classification. All right. So, and if you know that whether although P2 and P3 are looking very similar, and it is in the if we are having their class attribute information, if you are having their class level or class attribute information, then we will be knowing and seeing that most likely they are going to be the of the same class. Okay, so that's how the distances are helping us. If we generalize the Euclidean distance, we have what is called as the Minkowski distance. All right, so this is a generalization of the Euclidean distance. So if you look at that R, earlier what was the power of 2? Okay, so and 1 over power of 2 in the Euclidean distance. Okay, so this is now generalized for a large set of dimensions as well as for the number of uh, orders. Okay, and for various R values, you can see here that how we are having some very valid kind of distances. Okay, so this is quite a useful one. However, you based upon those measures, we can again take the distances between P1 to P4 and make the distance matrices again, and then you will be able to see that what kind of similarity is coming out. But the principle will be the same. That in the matrix you're going to look at that entry, which is the smallest one, and then you based upon the values in that entry, you will be able to say that which object should go together and which are a bit distant. Now here you are seeing one kind of a distribution of points in a two-dimensional plane. But here the thing to understand is that uh, we are now trying to understand that when there is that when you have so many measurements, there is always a difference between the values of those measurements, and then that there is a kind of a trend which can be visible. So as we have plotted so many points together, the trend which should be easily visible to you is that that A and B, if you join those 2 points, and you can say that most of the points are in a diagonal fashion distributed along the line which is joining A and B. Okay, and now if we want to detect or suppose we get a query that there is some new point P which is shown at the bottom right of that picture, that how that P is going to belong to this. Okay, so then this was a problem which was solved by PC Mahalanobis of India, and the distance which he has come up with is based upon is based on his name. Okay, so here you can see that the distance here between any two objects P and Q is found by this formula, wherein that sigma is referring to the covariance of the input data. All these sample points which you are seeing here, they find a covariance of that. That covariance is found by subtracting the mean and summing up all the deviations about the mean. Okay, and then standardizing it with the n minus 1 uh, number of samples. Okay, so that is the Mahalanobis distance. And Mahalanobis distance is actually used to be able to discriminate for even if there is a large variance in the set of points. Okay, so here you can see that uh, if we look at the distributions, so you can see that how the distances are can be computed. So the Mahalanobis distance from A to B is said to be is equal to 5, and the Mahalanobis distance from A to C is still less, that is 4. Okay, so here intuitively we may feel that C is closer to A, but as per the Mahalanobis distance, B is closer to A. Okay, that is because it is taking into account that there is a large spread which is all around C. I mean all around in that direction which is from A to C. Okay, so therefore keeping that in view, then actually uh, A to B is closer than the distance A to C. So in general, you have the properties of a distance. These are metric properties. I will not go into that. It is given in lots of mathematics and other textbooks. But these are the properties, and if any distance, if you create a new distance, you want to know whether it is a metric or not. You need to see that whether it is satisfying these properties. Similarly, you are having like that. You are having the similarities, and we say that if two objects are extremely similar, then their similarity value is 1. Okay, and you have symmetry and other such properties for the objects which are being compared for the similarity purpose. Now, a special case of this thing is the similarity between the binary vectors. Okay, there are very famous formulae for the comparison of the binary vectors. I will not go into the details of that. One example which is there is the Jacquard distance is given here. This is again quite useful when comparing tweets. Okay, will not go. Similarly, there is a cosine similarity wherein if you want to compare two documents and all that, you can compute their vectors, feature vectors, and then find out the similarity and compare like this. Okay, now on to the classification methods basically. So so we have seen that basic concepts. Now we can try to see that what else is there. So before we go further, I want to make it clear that we need to understand that what it means by the supervised versus the unsupervised learning. And as I said to you earlier, that according to me, the supervised learning is nothing but classification. So what is the supervision? So it is called supervised learning simply because there is a training data. Okay. And in this training data, as you can see here, as I'm showing here, you are having the observations and the measurements, and this is accompanied by labels. Okay, so if you don't have the class labels, then it will become an unsupervised learning. Okay, so that's why this labels is very important. Okay, so it's basically that it is a very trusted and important thing that what are the class label which is assigned, and because that is going to train your classifier and the entire approach for classification. Okay, based upon these labels which is there. Okay, so basically we can say that for supervised learning, we have to have labeled data. Okay, and based upon this labeled data, any new data will be tried to be observed, and it will try to find out and say that whether it is uh, the learning. No, so as per the learning, the data is going to be extremely important. So basically, the learning depends upon the data. That's all. All right. So unsupervised learning, we don't know, and just based upon some inherent properties of the data, we try to make some inferences and deduce that whether certain object should belong to the same class or not. And this kind of approach is also called as clustering. Now, what is the entire purpose behind this classification and all that? Now, see, what we are doing in classification is that actually, suppose you get a new sample, and we want to say that we want to be able to predict that this new sample, what is its class label. Okay, so what we try to do is that we are observing the space in which this class label is so we have ways in which we construct a abstraction of one class label and its space around it. And whenever some sample is there for its labeling, for the labeling, you're trying to see whether it is falling into that space or not. If it is falling into the space, then we can say that yes, it is belonging to this class. Okay, unfortunately, it is not so simple, and so many problems are there. But classification is extremely useful, and as you can see, this is very useful for credit card approvals, loan approvals, in medical diagnosis to diagnose from tumor or cancer, and you have some fraud detection and web page categorization and ranking. No, all the Google search it depends upon the web page categorization and ranking. So the Google has got a proprietary method which they will not disclose to anyone, and that is what they use to classify the pages, index them, and so the indexing is very important, so that so many millions and millions of web pages are classified, and then they are stored according to the classification, so that the retrieval becomes very fast. Okay, so if you spend computational efforts in retrieval, computational efforts in classification, then your retrieval will be hopefully faster or much swifter. Okay, that is the basic idea. So in classification, what we do is that first we have to do a model. We have to construct a model. Okay, and as we are having the class level information, it is required that we put together that information, and we see if there is possible to put a label attribute of for that one class. Okay, and all the labeled attributes which are, so you basically, what we do is that we divide into two sets. One is a training set, another is a test set. Okay, the training set class labels and their samples are used to classify, are used to train the model. Okay, to train the model. So you cannot have machine learning without the training the model. Okay, so basically that is the training which will be there. Okay, and then once we have a trained model, then we need to see that how good is that model. So to do that, we have to estimate the accuracy of the model, and when some other unknown test samples are being given, and what kind of classification it is producing, and that this kind of information, if we get, we'll be able to get to know that what is the accuracy of that model. So when training the models, one very important thing as shown in the last point here is that we want to have a training set, a test set rather, a test set which is different from the training set. Okay, so that it is actually going to be a real test, because the test set should not be known or seen previously by the classifier. Okay, so like this, when you train with various different parts of the training set, so we get to know that there is something called as generalization, so that the classifier is trained to generalize over the entire data set. Okay, and when new data comes in, these concepts will be used to categorize that new data, to classify the new data. Okay. Okay, so how do you build a classifier? All right, so what is classification and regression? These are the steps which are generally seen. So basically, if you don't have a class label, but we are just outputting some kind of a numeric value, okay, so then we are talking about a regression. Okay, or else we can do classification by the decision tree induction, or we can do Bayesian classification, or there are so many other classification methods. Say for example, SVM is an excellent approach by which the idea is to optimize the difference which is there between the classes on the boundary. Okay, so class imbalance problems and things like that will not be able to affect SVM. There are ensemble methods which are called as bagging and boosting methods. That is also there. Okay, basically here is that suppose you have a few unreliable means that those classifiers whose recognition rates are not so high, but still through the bagging and boosting methods, you will be able to combine them to be able to come up with a classifier which is higher than the individual classifiers in terms of accuracy. Okay, so now this is one of the methods of the supervised learning, which is called as the rule-based classifier. Okay, so here it is very simple actually. We try to formulate the if and then rules. Okay, and if the condition for that rule is satisfied, then we will say that yes, it is of this class or category, and we will keep it separately or whatever which is required to be done. So what is being done is that this is being viewed as logical formula, and condition is seen as a conjunction of attributes. Conjunction of attributes means it is all joined together by the and kind of logic. Okay, and the condition is implying that if the condition is satisfied, it is implying that the class label is going to be y. Okay, so that's the how it is. So the left hand side is the rule antecedent or condition, and the right hand side is the rule consequent. Okay, so like this, some kinds of say, let's suppose we are having birds, and we are having attributes regarding the birds. Okay, so how do we know something is a bird? That then it is blood type is it's a warm blooded thing, and it also lays eggs. Okay, so once we know that thing, then one can try to deduce that like what kind of um, inference can be had from that classification rule. This is a very typical example which everyone shows, wherein which is showing that how these rule-based classifiers are working. Okay, so this is quite a common example, and you can just see very quickly. You can see that how the categorization is there of some animals, and based upon the blood type, whether it is cold-blooded or warm-blooded, or whether it gives birth in a live once or not, and whether those things can fly or not. So like that, it is possible to build the first thing that and whether it lives in water or not. So like that, it is possible to build a kind of a categorization, which is that of mammals, of reptiles, of fishes, like that. So the what happens is that to build the classification, we must have the rules, and the rule will be covering that instance. Instance means an example, or a set of or a set of or a set of the data. Okay, wherein that attribute value is being used to satisfy the conditions. And so like this, the if there is some rule which is satisfying more instances, so that is a more powerful rule, which comes up to the question that there should be a test of the rule coverage and the accuracy, and you can see here how they are being defined. The coverage of rule is that the fraction of records that satisfy the antecedent of rule, and accuracy of the rule is that the fraction of records that satisfy both the antecedent and the consequent of a rule. I am just showing one example here. Okay, I don't think so. It's really necessary considering that we have so much to cover. So quite a straightforward thing to see that how these rule-based classifiers are working. So the rules in the rule-based classifier should be mutually exclusive, and they should be exhaustive in the sense that exhaustive, it should cover every possible combination of the attribute values, and it should also make sure that all the records are covered. So that is one of the records is covered by at least one of the rules. Okay, so if you don't have that coverage, then that will not be possible to classify that record. Okay, so so if you want to make sure that everything is getting classified, so then you should have this that each record is covered by at least one rule. So do we have a decision tree? Yes, from the decision tree we can build rules, or from the rules we can build decision trees. Okay, so this is the important thing to understand in the supervised learning methods, that if you have a you can take the rules, and then given the data you can build a decision tree, or the other way around is that uh, the decision tree is being built. They build it anyway, and the validation of that is going to come from whatever is the data which is available. Okay, so here one example is shown, and this is a fairly common thing nowadays. And the idea is to get a description of the rules, which is a very simple description. Okay, so I'll skip these details which are about the rule simplification, and because then we are to go on and go on to more kind of things, So sequential covering and all such kind of things are very important concepts when it is related to the rules and the samples which are there, and whether the rules are covering all samples and things like that. I'll skip these aspects. Yeah. Okay, so I need to go forward, so I'll be skipping this. Now, how for every classification or for every supervised learning, we need this metrics for accuracy or evaluation. All right. So, how good is a rule? All right. So, there are some. These are some approaches to look at the accuracy of these rules. Okay, so we have that how do you stop building the tree? So that is a stopping criterion for, and then how do you remove some rules? These are some things which are there for that. Okay, I'll again skip these things, and there are some softwares which are built like Ripper software, which is meant for these kind of things. And then one of the another approaches is a very famous C 4.5 way for building the decision trees. Okay, and nowadays this is a lot of software is there, and if you search for that C 4.5 kind of classifier, you will get the source codes, etc., for those classifiers. So that's why I'll just skipping that, and you can see that how these uh, different types of the methods to build the trees can be there, and how they're in what way they are competing with each other. Okay, so some comparison is also shown here. So finally, why do we want rule-based classifiers? Although it's very old kind of thing, because it is quite expressive. It is very easy to do to interpret. Very it's easy to generate. Okay, and if there is somebody new adding new instances, we can very easily classify those like that. So that is the basically the idea. Okay, I think I should try to cover other methods and approaches also. Let us skip those things, and we are um, decision tree induction also. So now this is a very well-known method, which is of the entropic approach to build a decision tree. So what we do is that we are looking at the attributes, and we are trying to see that where is it that there is a highest conservation of the information. Okay, so if we build the if we, or if you build a split, or we make a rule and it splits the population, so in what way we are going to conserve this information? So highest information gain, and these things they depend on computing the entropy of the set of values, and from that we try to maximize the entropy, and like that you do that, and that is the method behind, I mean, that is the idea behind these ID3 and C 4.5 approaches. And you can see that how their formulations are given here, so that how the gain is formulated, and how we compute the information, and how do you get the expected information, and that is how we can compute the gain, and by maximizing the gain we are able to build the decision trees. Okay, so again some example is given here. I'll skip that. You can easily see that some computations are there and how it is being computed. Those formulae which I had shown earlier, that is what is being computed, and they can show that, for this example, what is the best way to, which is the important way to divide this. Okay. I'll skip these things. So when we are comparing these attribute selection approaches, we are seeing that the performance measures is like a gain ratio or a Gini index, and these are the ones which help us to evaluate this classification classifier, which is based upon the attribute selection. Okay, so many other attribute selection methods are there. We need not go into that, but one thing I will stress is that minimum description length principle is a very important principle, because it is better to find, if you are able to find that attribute which is giving us a more simple description of the data set. That is, then we think that that is a kind of the best way to go about it. Okay, so overfitting and true pre-pruning and these kind of things are very specific to the problems which are there for decision trees. Okay, I'll skip that as well, and let us see. We can skip this as well, and we can go to the nearest neighbor classifiers. All right, and okay, the idea is that if you are seeing that that the neighborhood is very important basically. Okay, so if you are in the company of ducks, then you are most likely to be called as a duck. Okay, so you can see that the basic idea is very simple, that you come up with the representation of each object, you compute the distance, and you compute the distance to the test one, and then you see that whether it is having the same label or not. If it is having the same label, then whatever is that label, you have to classify it with that label. Okay. So how do you do that in more formal way? So you require that the entire data set be available. The class label here is very important. Okay, so because that's how you'll be able to know that what is the kind of uh, classification which is being given for the training set. All right. So like this, you will be able to come up with the ways to classify, and you can suppose you can even then use the nearest neighbor classifiers to build some decision rules also. Okay, so based upon the various instances and the distances between those patterns. Okay, this is basically overall overview of what is the nearest neighbor classification. So you compute the distances and you find out the class from the nearest neighbor list, and you take the majority vote of the class labels from the k nearest neighbors. Okay, there are many ways of this. You can have k nearest neighbors. You can have only k equal to 1, that is the nearest neighbor approaches and things like that. K nearest neighbor is supposed to be very robust. Okay, in a large statistical sense, it is supposed to be able to give us the classification which is with the least error rate. Okay, there are some very serious proofs about that in the important pattern recognition textbooks like Duda and Hart and things like that. So, but it's too much to go into those proofs, etc. now. Generally, the very common sense thing is that k is to be chosen such that k is odd generally. Why? The reason is because if there are ties, and with the odd numbering, you can break the ties. But if it is even, then you will be left with a tie, and you don't know how to break the tie. So the neighborhood value should be sort of tuned very carefully. And if it is too small, then if there are some noisy points, then it might not be able to focus in on the broad one, and it will be just going according to the noise. But if it is a very large one, then it might not be so sharp, and it may include the points which are from other classes as well. So that's why you have to carefully choose this value of k. And you have to standardize that, after all, in the nearest neighbors depends upon the distances between the attributes. So we have to make sure that the scaling is constant. Okay. Okay. Now here let me show you one very important concept in all this classification and supervised learning and all that, which is called as the curse of dimensionality. You can see it in red over here. Okay. And this is a very interesting example wherein you can see two binary vectors. Okay. And the two binary vectors, basically they are having a very little difference. Okay, they are differing just by 2 bits. Okay, they are differing just by 2 bits, and you can see that here, that uh, so a similar kind of ones is there. All right. Now, when we take the distances and the sums for these two sets of, this is one set of vectors, another set of vectors. And as you know, and you can see, what is going to happen is that this set of distances is just going to be 2, whereas this set of distances is going to be a very much larger number. All right. Okay, so this distance is 1.4142, and this distance is also 1.4142. So because it is so, despite all this number of ones and all that, you can see that the distance is the same. All right. Okay. So what is to be done? You can normalize the vectors to be of the actual unit length. So if you divide that by n, you can get a number which can be more, because everything will be then within the 0 to 1 kind of a range, because we are doing normalization. So that will be much useful. Okay, so the term which is used is that the k nearest neighbor classifiers are called as lazy learners. Why? Because they do not build the model explicitly, and the decision trees are eager learners because they want to very quickly they want to make a rule. Okay, but the nearest neighbor is lazy; it's not trying to make a rule. Okay, so therefore, as you get more and more samples, then the classification will become very expensive, because you have to go on computing the distances to all the samples. Okay. Now we take up one more approach, which is called as the support vector machines. So in the support vector machines, the idea is that you have two classes, and we are trying to find the decision boundary, which way that decision boundary should go, and we want to make the decision boundary to go in such a way that it optimizes the distance between a set of samples, which is called as the uh, which is called as the ones which is the support vectors. Okay, so as you can see, the decision boundary can be having many different slopes. Okay, and still be classifying correctly. Okay, but which of these decision boundaries is a better boundary? How do you decide that? Okay, so that's why in the support vector machines, and notice here that it is irrespective of how many patterns are there on either side of that boundary. Okay, so it is not like a statistical weighted measure where if there is an imbalance in the classes. Okay, these days class imbalance problems is also a very important research area. So the support vector machines are good because you can use them despite the class imbalances problem. Okay, because here what it matters is that you are concerned with maximizing the margin. All right. So many solutions could be there, but here we are trying to maximize the margin. Okay, so this way we can see that this is the margin, and what is margin? Basically, we want to get the maximum distance, so a perpendicular distance from the hyperplane, the boundary hyperplane, to the nearest set of points, okay, which is on the margin. So those are the marginal points, and with respect to the marginal points, we want to maximize the distance, okay. So this is how these distances are seen, and the classification is given that it is said to be +1 if it is on one side of the decision boundary, that is given by the weight vector times the x value in the decision boundary, okay, plus a bias which is called as b, and okay, so then what we try to do is that we'll try to build a optimization, okay. We have to build an optimization with the constraints of these boundaries. So there is a constraint optimization problem, and you have to solve it using some quadratic program, and lots of mathematics is there with this with respect to that. Now, question which people ask is that what if the problem is not linearly separable? All right. So for that also there is something which is called as kernel trick. So what they do is that using the kernel trick, or what they do is by introducing some kind of additional set of variables, you are projecting these points into a higher dimensional plane. In the higher dimensional plane, then you are trying to find out what is the solution to the optimization of the boundary, that is the margin, and then once you get a solution there, you will map it back to this lower dimensional space. Okay, so and this will work, even if the decision boundary is not linear, and like that. So here it is just showing that how you can do it is transforming into the higher dimensional space and then coming with that. Now the last one, which I think I don't have much time. The last one here is that is a Bayesian classification methods. This is a highly statistical based approach, and it is based upon the Bayes theorem. And a special case of this is called as the naive Bayes theorem. Okay, the problem which is there with this Bayesian classification is that you need a lot of data to be able to collect all the marginal probabilities when it is all the marginal probabilities and densities when we are trying to build the classifier. Okay, now uh, a solution to that problem is that you simplify and build what is called as a naive-Bayes classifier, and it is shown that somewhat the naive-Bayes classifier is comparable in performance with some other non-classifiers like decision tree and some small set of the neural network classifiers. Okay. And Bayesian classification is good in the sense that as you get more data, you can improve your hypothesis, and each of these data items can be used to increase or decrease the probability that the hypothesis is correct. Okay, and the standardization is there with the Bayesian classification, because the Bayesian theory allows us to do a classification which is minimizing the error. Okay, so basically this is the Bayes theorem, and everybody who has read the statistical classification textbooks would be knowing that how this is. So on the left hand side, it is called as the posteriori probability. So H is standing for hypothesis, okay, and X is the data. Okay, so here the priori information, which is in the training set, is on the right hand side. Okay, so that training information is there, and that when you give some new data sample, it is put into that, and then it allows us to compute the probability for the various hypotheses. And then the Bayesian classification is very simple. It is nothing but a maximum probability classifier. Okay, so and there are lots of proofs which show that the maximization of probability, a posteriori probability, is actually minimizing the error. Okay, so there are lots of proofs for that. So everything is fine with Bayes theorem except for that the dimensionality problems and the so many probability computations. Okay, so that I have given here at the bottom. Okay, so and as I said, the classification is based on the maximum posteriori probability. And what happens with the naive-based classifier? In the naive-based classifier, we are simplifying the assumptions. Basically, we are coming up with the assumption saying that the attributes are conditionally independent. So when things are conditionally independent, the probabilities can be found just by taking a product. Okay, so the conditional probabilities will then simplify and it will all become into the products, and that is how the naive-based classifier will be able to compute the probabilities and come up with certain answers. Some examples are shown here, and of course zero probability problems are there. Okay, I'll skip that. Now we are on to this model evaluation and selection. It is 3 o'clock now. I can request the organizers that how much more time I'm having to be able to speak.
You have 45 minutes more, sir. No problem.
Oh, I have 45 minutes more from now.
Yes, sir.
Okay. And does that include the question and answer, or that is the additional?
Additional, sir.
I see. I see. Okay. 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 I'm happy to know that so that I can dwell more on these things.
Yes, sir.
Thank you. Now we are on to that. What is this about? We know that now there are so many classification approaches. This is just a small glimpse of the various classification approaches. How do we evaluate these? So to evaluate these, we have to have this model evaluation and selection approaches. Okay, so what do we do is that we have to have some validation tests. So these are like the statistical hypothesis tests. And here also we can do the subsampling. That is, you hold out method, which is that you don't use the entire data set, training set which is there, and then you hold out means you don't add it into the set which is being used to train, and then you compute the classifiers and all that, and then you may use this to be able to test and see that how the performance like that, and then you can fold it up. So that is what takes place in the cross fold validation. All right, or then you are having the bootstrap approaches. Bootstrap approaches are highly statistical approaches in which with it is like a sampling with replacement. All right, and using that, then the statistical models are built. And how do we can compare the classifiers by looking at the confidence intervals which are being produced, and we can compare the classifiers by the ROC curves. So these are the methods which are there to estimate the classifier accuracy as well as to compare the classifiers. Okay, one of the important things is that whenever you do classification, we can get an output which is the confusion matrix. And this is the, for any set of classes, we can get a confusion matrix, and in which these four categories are very important. Okay, the four categories are that you have true positives. Okay, that is, true positive is that it is a correct classification. That suppose I'm labeling the birds. So then the true positive is that a new sample came in and I have labeled it correctly. Then you are having what is called as false negatives. Okay, false negatives is that uh, we are insisting on classification that this is not a bird or something like that, but in reality it is a bird. Okay, so that is our claim that it is not is false. Okay, so that is called as the false negatives. Then again you now have another one which is called as the false positives. So in the false positives, it is that it is actually something else, but we are labeling it as belonging to one particular category. Okay, so if that category is say C1, all right, so then, and it is sorry, and it is not actually belonging to that class C1, then it is under the set of the false positives. Okay, and then the other one is that which is actually that which is the true negatives, that it is not C1. We know that it is not C1. We have labeled it as not C1 and it is actually not C1. Okay, so that is a true negative. So basically it is this diagonal which is very important. This diagonal is indicating that there is no confusion. But if you are getting more of the false positives, more of the false negatives, then it is indicating your classifier is not doing well, and there is a confusion. All right. So that is the kind of thing. Okay. So that's why in all these supervised learning and classification tasks, we can build a confusion matrix, and that is allowing us to be able to evaluate that whether our classification approach is able to give the results which we are expecting or not. Okay, so if you see more of the off diagonal elements, it is an indication that your classification approach is not so good. Okay, that's a very simple approach to see. Just do the classification and build the confusion matrix, and then count the off diagonal elements. You sum up the off diagonal elements and you compare that sum of the numbers with the off diagonal elements with the ratio of the on the diagonal elements, and then if it is a good ratio, then it means that you are doing well. Otherwise it's a bad ratio, and then you have to go back to see that what is going wrong in the classification. Is it the features which you have selected, or it is the classification approach which you have selected, like that? So then you will have to debug. Okay, so as you can see here, how do you calculate the classifier accuracy? So, or it is also called as a recognition rate. So it is a percentage of the test set tuples that are correctly classified. So what is that? As I said, we are going down the diagonal. So that is true positive plus the true negative. True positive plus the true negative. And that is divided by all. That is all the positive and negatives. Okay. And what is the error rate? Which is that it is 1 minus the accuracy. Okay. So that is giving an error rate. All right. What do we have in the class imbalance problem? In the class imbalance problems, what happens is that in the sample set, which is no, see, as I told you that sample set is very important for training. Okay, but in the sample set itself, we may not have sufficient members of one particular class. So that will be called as a class imbalance problem. Okay. So, for example, let us say that if you are taking blood samples, okay, so blood samples that only a small percentage of people may be having the HIV disease, okay, so but still it is a very important disease in the sense that once somebody gets the disease, there is no cure. You have to go on taking the HIV retrovirals throughout life. Okay, so you're not going to die of it these days. Earlier people were dying of that, but nowadays they are having retrovirals, etc. Some HIV treatments are there, which if you go on taking for your life, you can uh, survive. Okay, but so that's why if you are doing HIV classification, it is very important to be careful, because you know you can't uh, afford that risk which of that being so, because HIV being so deadly. All right. So significant majority and negative number like this, we can compute some other performance measures. As you can see here, the performance measure which is called as sensitivity. Okay, so sensitivity is that you take the ratio of the true positives over the entire set of those samples, which is classified as being positive. Okay, so that's the sensitivity. So if you have lesser number of true positives, your sensitivity. If you have true positives, your sensitivity is okay. Then there is one more other measure which is called as specificity. So specificity is that you are taking the negative examples. You take the true negative examples, and you see that what is the true negative recognition rate. Okay, so then it is seeing that how specifically we are able to tune out and say that it is not belonging to the class which we want to look at. Okay, so that is given by the set of true negatives divided by the actual number of true negatives. So as you have seen here, so it is that we are now you are building a classifier, and then you are having some method to be able to gauge that how is that classifier doing, and based upon that you might be able to see that fine tune that your classifier and see that in what way it is not performing as expected, and it should be then set right. Okay, so that's how it can be. Okay, then we are having some other performance measures. Okay, these are all very important performance measures where all our things which are there, we are using these measures to look at the performances of whatever classifiers which we are having. So the first one is called as precision. Okay. Precision is also meaning the exactness, meaning that what is the percentage of the tuples that the classifier has labeled as positive, and as compared to those which are actually positive. All right. So what is actually positive? If you will recall, and we go back to this matrix, so you can see in this matrix that what is actually positive is that it is the true positive and false positives. Okay. So when you are having the true positives, so now if I get a very large number of false positives, what is going to happen? You can see that the precision will fall. All right. So I should have very large number of true positives, and ideally false positives should be 0. So in which case my precision will be equal to 1. That is a high precision. Okay. What about recall? Recall means that completeness. That is, what is the percent of the positive tuples that the classifier did label as positive. Okay, so now here it is that I want to reduce and see that the false negatives should become 0. Again, this will be, if it is closer to 1, it is better. All right. And there is actually the inverse relationship between the precision and the recall. Okay, and you can have some kind of a score which is called as the harmonic mean of precision recall, and if you can see that the F score is 2 times the precision into recall upon precision plus recall. Like the F score, there is one more measure which is called as F beta. And this is if you are having some weight beta, so you can use that. So instead of 2, you may be able to put it as 1 plus beta square into precision and recall. And in the denominator, it is beta square times precision and recall. Okay. As you can see that if the beta is close to 1, then you are the same as the F score value. Okay. So this is just some kind of an example for some data where these classification evaluation metrics are being used and the various figures have been calculated, sensitivity, specificity, accuracy, etc. Okay. Now, what about a holdout method? So you have the two methods, that is the holdout method and the cross validation method. Uh, in the holdout method, what happens is that uh, we are taking the data, it is randomly partitioned into the independent sets, and then we will apply the classifier on those sets, and later on we'll be seeing that what is the accuracy on that. All right, and so with this, what happens is that in the independent sets, you will be using one part of that for the model construction. Okay, so that will be called as a training set. And then how good that model is performing, then you will be using that, and that set will be called as the training set. I mean the test set. All right. So you are going to use the training set to build the model, and the test set will be there to see that how good is the model, and they get the accuracy of that performance. Okay. Uh, one another way is called as the random sampling, in which it's a variation of the holdout. Okay, so then you can repeat the holdout k times, and get the average of that. So that is actually a better way, because as you're randomly repeating, all right. So it is not biased towards any particular training sample, all right, and it is, as it is a random one, so it is being averaged out over the entire set of the data. Okay. Another one which is called as the k-fold, where k is equal to 10 kind of thing is pretty popular, and that's the random partition into the k mutually exclusive subsets, which are approximately the same in size. You can have leave one out, and you can have some other strategies like stratified cross validation. So that is, you can have a hierarchical approach wherein the folds are stratified. So the class distance in each fold is approximately the same as the initial data. One very interesting approach, actually there is a lot of statistical kind of thing in that, but I'm not showing you that, which is called as a bootstrap sampling. Okay, so bootstrap sampling is that it will work with the small data sets. We don't have enough data, but still we want to estimate some probabilities. We want to estimate, get some estimate that how some classifier etc. will perform when we get more data and things like that. So what they do is that with the available data, they take the samples, and they sample uniformly with the replacement. Okay, so that is, you can select some data item and put it back into the population, and like that select something, and like that, and go on replacing. So like this, you have this sampling, and that is supposed to give us some representative picture of what kind of data set you have. Okay, so that is okay. So if it is you have d tuples, you can sample it d times with the replacement, and that will give us the training set. And roughly you have a formula estimate, which is that 1 into 1 minus 1 over d to the power d. Okay, basically that is the kind of thing, and there are some formula etc. behind that. So that is saying that how you, if you repeat this sampling so many times, you will get some overall accuracy. Okay. Now you also have one measure which is called as a confidence interval. And if you have two classifiers, which is M1 and M2, and you want to know that which is the better one, okay, so what you do is that you try to use the tenfold cross validation, and then you look at those errors, and then you try to find the differences, and you try to see that whether that is a significant or not. So then you use a test of the statistical significance, and you try to get a confidence limit for the error estimates. Or there is something which is called as a null hypothesis. That the null hypothesis is that they are basically the same, all right. But if you reject the null hypothesis, then you will be able to say that there is some difference between them, and that it is statistically significant. So these are all well-known statistical tests, but we need to use that to be able to estimate that how well our our classifier which we built is doing. Okay, there's one more test which is called as the t-test, and this is also well known, and you can see here what is the formula for that. How do you find the t value? So basically it is that you get the average error differences, and then you sort of take the uh, you try to normalize it, the average error, you try to normalize it with respect to the variances, the differences in the variances. All right. Uh, so if the differences in variances is more, okay, so then that will be the even the errors etc. will be there, and it will be reduced. Okay, so the t value gets reduced. Okay, and this is a well-known statistical test, and you can see that with respect to some kind of a normal, the t distribution is there, and how it is table is there, and you can see like a normal distribution kind of thing. You can calculate that and see that what is the confidence value. Okay, so I think this I already covered this. Ah, so there is one more way in which you are comparing the models. So that is, it's called as a ROC curve. ROC curve comes from the name which is called as receiver operating characteristic. Okay, so this is for the visual, it gives a visual comparison of the classification model. Okay, so and on the right you can see the curve, the ROC curve, wherein you are having on one of the axes, that is on the x-axis, it is plotting that false positive rate, and on the y-axis is a true positive rate. Okay, so and then you can see that when the false positive rate and the true positive rates, if there is no bias etc., it is going to be along that line. Okay, so it shows the trade-off between the true positive rate and the false positive rate. Okay, so if it is a flatter curve, it means that the false positives are higher, and the area which is under the ROC is the measure of the accuracy of the model. So the closer it is to the diagonal line, the less accurate is the model. All right, and if the model is perfect, then what happens is that this line which is seen here is very close. It is just going like this. Okay, practically you won't see it like that, but if it's a better model, it will rise up steeply like this, and then very closely very follow this value to the 1. Okay, and maybe exponentially or whatever it will reach there. I don't know what happened. This screen has. Okay. All right. So what is the problem with respect to the model selections? Is that you have to take time to build the model, the training time, and you have to use the model, get the classification and the prediction, etc. All these kind of things are there. So that's why the model correct model selection will be taking us time. Now, how robust is the model? How much of is there? Sometimes you have in real world situations, we don't have complete data. Some of the attributes may be missing. Okay, so how robust is the model? Okay, how scalable is it in terms of the computational complexity? If suddenly the number of samples doubles, triples, 4 times, 10 times, then okay, is it still viable and we can use the same model? Okay, finally, that what is interpretability? That whether the understanding and the insight is stored in the model is sufficient for that. Okay. So with that, we have come to the last part of this. That is that how do we improve the classification accuracy? So for that, the answer is the ensemble methods. Okay. So in ensemble methods, what you do is that you will construct a set of classifiers from the data which is available, and you will be trying to predict the labels of the previously unseen samples by aggregating the predictions which is made by some of the other classifiers. Okay, so like that, whatever is learned about those classifiers is used to the maximum extent. Okay, I'll just show you what it means. So what is the general idea? What you do is that you'll suppose you have a fairly large training data. Okay, it will work better if you are having very large training data. You will partition this. The training data is partitioned into various sets, and the various built, and then into that
NPTL ஒன்னு படிச்சிருந்தா தெரிஞ்சிரும் எவ்வளவு
classify.
கஷ்டமா இருக்கு தெரியுமா படிக்கிறீங்க
So on each partition of data, data
ஏன் ஒரே ஒரு ஃபைல் வீக் 1
this classifier, and then you are going to obtain the results. As you are getting different classifiers, you are going to get different results, and then you have to have an approach by which you are going to combine all this data of the classifier of the classifications. What is the idea here? The idea here is that the various different classifiers might have different defects, and they may also have different kind of strong points, and so that the overall strong points and defects which will come out will be stronger than the individual classifiers themselves. Okay, so it does work because if you have the classifier array as something, and then the product is, we can see that the probability that the ensemble classifier is making a wrong prediction will be multiplied with that, and the summation for all the classifiers, so that is going to give generally a small value. Okay, so there are two well-known methods, which is called as bagging method, other is called as a boosting method. Okay, for the boosting method, ADA boost kind of approach is well known, and it's a very strong approach. So what do we do there? So in the bootstrapping, we are having the small sets, and we can do the uniformly with the replacement, and 0.632 times that value, that is a bootstrap rate, and so you can do a sampling k times, and you will get an accuracy which is given by the summation of over all the k folds of 0.632 times the accuracy plus this 0.638 times the accuracy of the training test set and trainings, like that. So if you sum it up, you will get that. Now you also have bagging, and you have the bagging rounds and all that, but boosting is somewhat more popular. Basically, boosting is that you are using an iterative procedure to be adaptively changing the distribution, and you are looking at the previously misclassified records. Okay, so here is just trying to show that how this boosting etc. is working, and ADA boost algorithm is also shown here. You can have some t number of base classifiers, and then they can have a different kind of an error rate, and then here after combination you get a weightage for each of these classifiers, the alpha I. Okay, so that is given by this value. Okay, and it can be updated also when we get the results. Okay, so and the resamplings can be done so that you can redo it and get the results again. Okay, there is actually an algorithm, a step-by-step algorithm is there, which tells us how to do the ADA boost. Here is just giving you a mathematical overview of that, how it should be working. Okay, so you can see here this, I think I have already talked about this slide. Okay, So ensemble methods are increasing the accuracy, and this another word is like a voting approach. Okay, so it is combining the votes and then giving the class prediction. Okay, bagging is the bootstrap aggregation. I think so. I've already spoken about this. Okay. This is the AdaBoost approach, as I had mentioned earlier. And process is given here. I am trying to rush through this, and so that I can also talk about the random forest. Actually, it's very amazing that just like you're having decision tree. Now, suppose I randomly construct different decision trees. Okay, if I randomly construct various different decision trees, then I will be able to get what is called as a random forest. And it is shown that that the random forests are able to come up with very good overall results. Okay, so you can there are two methods for the construction of the random forest. You can see that how the it will be a usual method to grow the decision tree, all right, but as it has been explained earlier, you are dividing up the set of candidates. Okay, so that's why uh, each random forest will be somewhat different, and some pros and cons are there for that. And always the class imbalance data sets are not so easy, and you can have problems which are related to oversampling, undersampling, and some decision thresholds can be moved. All right, so because of that, okay. So let me summarize that. We have seen an overview of these supervised approaches, classification approaches basically, and decision tree, naive-based classification, rule-based classification, and the evaluation metrics we have discussed, the k-fold cross-validation methods we have seen. Okay. Now I will switch over and like to show you some other kind of literature. Let us see if I can um, do that, and let us also try to do one more thing. I have I don't know why this keeps coming over. It is not allowing me to. Actually, I want to switch the window. Okay. So see, you have seen theoretically that the supervised classification and all that, but I have worked practically on building a Telugu OCR. Okay, so let me just give you some insight on that. So OCR is actually optical character recognition. All right. So let me show from this slide. So you can see that I have talked about what is the optical character recognition. It is a process by which you take an image, and whatever is the printed matter in that image is recognized, and it is made into a symbolic form. Okay, this the basically the OCR process. Some various image processing operations are there. We do scanning, binarization, uh, and after that we segment out the words, we extract the components, and we normalize those inputs, and then we extract the features, and then apply the classification and recognition, and then we do a post processing and encoding. Okay, and there are so many applications of these, and there are so many OCRs which have been built for the various Indian languages. We have built at our University of Hyderabad, we built it for Telugu. Okay, let me show you some examples of that. So there are so many approaches for building the Telugu OCR. Structural approach is there, neural network approach is there, template matching approach is there, wavelet based approach, multi-resolution approach is there, like that. Some previous literature which is there in that. Okay. Telugu script is certainly difficult, and because it's a rounded one, no? And this is the features of Telugu script. Those who are native speakers will be knowing that you have this achulus, hallus, matras, ottus and all. And let me show you that what we did was that in our first important paper, we have made it such that we reduced into a problem of 10,000 instead of 10 recognizing 10,000 symbols, we reduced it to problem of being able to recognize 400 gifs. Okay, so this is some examples of that. Okay, then this is one more approach which was there previously, which was based upon the feature extraction, and then here from images we were trying to find out the whether or not there is a Telugu character, and then recognizing that character. Okay, so this is from one of the India Today magazine. You can see it's a difficult example because there is some picture and the text is superimposed with that picture. So first we have to remove that text, we have to remove the picture and see that it goes away, and then only we are left with the text. Okay, so we have identified all the text, and this text is then recognized, and the recognized text is through after noise removal etc. is placed and it is recognized. Okay. And how do we do recognition? One of the methods for recognition is that we have built a recognizer which is based upon template matching, and the feature is the fringe distances. Okay, so the fringe distances allow us to compute that. It's not possible for me in this limited time to explain what is fringe distances, but that is how we have used. It's actually applied on binary images. Okay, so as we were using binary images, it is useful on the binary images. And this is our overall approach. And let us see that we had some kind of a testing tool as well. And let me see, there is one table in which this is another method where we have non-uniformly sampled the input characters. Okay, so that helped us to. Okay, in this table you can just get an idea. That what all are the glyphs which are there, and how it is. So we have built up each of these as a class, and we have tried to recognize that. Okay, so this is and you can see that how for each class the distances are there, and how it is working on a minimum distance kind of an approach. Okay, here it is a working example of a minimum distance classifier. Okay, these are other ways of doing the feature extraction and finding out the distances. Okay, so these are some other ways for doing that. All right, I think that's enough for this, just to show that as an example how do you use the classification approaches, or how the supervised approach for say recognizing these characters is used. Let me switch to some other kind of a example. Okay, let me switch to one of the windows. Sorry, not this one. Okay, here I have found one of the references, which is just to give you some overview, like what is there in literature. More or less, we have gone along in that way. Okay, so in this overview, if you see, this is visible, isn't it?
Yes, sir, it is visible.
Okay, correct. You can see here that in this survey article, this is a survey article. It is from the ResearchGate, and people can find that. Just if you type in, I had shown that beginning part. You can just maybe perhaps note this one. That is overview of supervised machine learning approaches by Vladimir Nastisky. Okay, so if you put that into Google search, you will come across this article. Okay, So this is a good article in which he has given and he's looked at all these aspects. What is supervised learning, unsupervised learning, semi-supervised learning, okay, reinforcement learning, and some kind of an approach which is called as transduction and things like that. Okay, so this is one of the other um, reviews of that. I have put it here just for people to know and understand that there is a lot of work and people are made some good efforts and surveys. Okay, and this process of that and all that is explained. I think I have already explained this kind of thing. It's the same thing everywhere. Okay, let me try to switch over and show one more thing, which is this is a book, and as you can see, the name of the book is The Elements of Statistical Learning. Okay, so this is a very serious kind of a book, and what I have here is that I have put together the table of contents. For the purpose of being able to show you better, I am trying to zoom in on that. First of all, you may note the names of the authors. Elements of Statistical Learning by Trevor Hasty, Robert Tibishirani, and Jerome Friedman. Okay. So they also start with overview of the supervised learning. They include linear models, nearest neighbors, least squares, statistical decision theory, okay, like the Bayesian decision theory, etc. Okay. Then they have various. Then they go into all the methods in detail. Linear methods for regression, in linear methods for classification, the basis expansions, kernel methods, model assessments and selection, model inference and averaging, like that, additive models, trees and the related methods. Okay, boosting, you can see that boosting is given in this book.